Hi, Richard Walding here from Brisbane, Australia. I'm just going to run through a couple of pracs I did, or it's part of a presentation I did for the University of Queensland and for Griffith University for teachers' professional development. I'll just show you the starting slide because it sort of details what's going on. I've called it Two Great Faraday's Law Pracs, and I'm going to do actually a couple more than that, but I'll just go through it. It's fairly simple equipment, and I'll run through that and then I'll show you the pracs. Okay, let's have a look. The equipment you're going to use is I'm using is fairly simple. I'm using a coil, this is a 1200 turn coil, but you can use simpler things than that. Like for instance, I've also used just a spool of wire. It's probably 100 meters or something in there, and that's fairly cheap. That's only about $10. I'm going to use a digital crow. This is the USB crow. Now they're expensive. You can get them for about $200 at JCar, but they're a lot cheaper, online. You can get them straight from China online. And of course just an ordinary old coil, air cord solenoid. You can use that, and also just a simple, this is a microammeter, just an analog one. Some schools have got those. They don't have the crows. Okay, so let's get on to the main part. Now, the equipment I'm using to set it up is fairly straightforward. It's just a digital crow which is plugged into the USB port of just a laptop. That's all I'm using, and you can see in the diagram I've got that. It's a 1200 turn coil. It's got a ruler. Here's a little magnet. I didn't show that before, but it's just a little magnet. Now it's a rare earth magnet, but I've painted it red and blue just to make it easier. And students often mislabel the magnets, and they don't consistently use the same end going in to any of these experiments. Okay, so that's basically my setup, and so we'll run through this. Now in Queensland, and this is particularly for Queensland, I'm doing this presentation. The syllabus for 2019 and the new syllabus coming out has a couple of content items that students will need to address. The first one is describe the process of inducing an EMF across a moving conductor, and that's the key part of today's work, and solving problems involving electromagnetic induction using those two laws. They're from the syllabus, and the second law, of course, is the conventional way of writing. Well, they're both Faraday's law. Okay, now normally if you're not doing this as a student experiment, you're just doing it as a demonstration, or the students are doing it, the simplest process is to use a coil, an air cord solenoid hooked up to some sort of meter, a millivolt meter or a microammeter, and just put a magnet in and out of it. So this is what I do at my school. In slowly you get a certain reading, in fast you get a much greater reading. Okay, now that's good as a demo, but you can't really make it quantitative. It's not easy. You're controlling the speeds and so on. Okay, so what I'm going to look at is the first experiment, which is to do with letting a magnet fall through a little loop, a coil. So there's my magnet, and I'm dropping it from a certain height h through a coil. Now that's the first step. That's right at the beginning. Then you can imagine after it falls through distance h, the magnet's approaching the coil, so the flux is increasing inside the coil, and you'll get a rising EMF. Okay, and that'll show up on either the voltmeter, or if you're using a digital crow, it'll show up as a curve on that. The next step is when the magnet is right in the middle of the coil, so it's at its maximum EMF at that stage because the end of the magnet, which is the highest magnetization, has just moved through the center of the coil. So it's going from maximum in one direction, and now it's starting to move out of the coil, if you like. So there's going to be a big switch over of voltages. So that's where you get the maximum voltage. And the third, and for my setup, you'll notice there's a difference between H and S. H is actually the ruler height between the bottom of the magnet at the start and the top of the coil, but the coil has a certain thickness, so I've had to add a little bit on just past the center of the coil to get the sort of fall distance, if you like. And then finally is when the magnet is starting to leave the coil, so it's gone past the surface has gone past the middle, and now we've got the actual middle of the magnet in the middle of the coil, and so the EMF drops back to zero. So you can imagine we're going to get a curve for this, and it's just a typical sine wave, so I'll just show you those. So at the start, there is no voltage. This is the EMF up the side here in the y-axis, and time along the bottom. So at the beginning, the EMF is zero. So when the magnet hasn't been dropped, the EMF is zero, but it's going to follow that sine curve. So in the next diagram, when it starts to fall, the voltage will start to produce a curve up the first side of the curve. It looks like that. So on the digital crow, or if you could take readings somehow, you'd get that sort of shape starting to rise. When you're at the maximum point, that's where basically the part of the curve you're at, and then the next one is it falls back to zero, and you see that. So what you should see on the crow is that waveform as all of that happens. Now it's the maximum EMF that we're interested in. That's the easiest one to measure, and that's what I'll be doing, and that corresponds to when the magnet's fallen a distance s, which is h plus whatever width of your coil. Now if you're using a single loop of wire, h and s would be the same, but the problem with a single loop of wire is you're not going to get the voltages big enough to really display cleanly on a crow. So let's see how we go. Now just to talk about some of how it fits with Faraday's law, what I'm going to do is just consider when I'm getting the maximum EMF, and so the face of the surface of the magnet is just past the middle. So I'm looking at a region when it travels a distance delta H. Okay, now that delta S. So that little bit in the middle is where we're getting the maximum EMF, just as it goes from the top of that line to the bottom, roughly in the middle of the two magnets. Now I'm not measuring that, I'm just saying that's a constant value. I'm going to keep that in my head as a constant value. The change in magnetic flux, delta phi, will be constant over that range because the magnet is not changing, it's just changing position, but the surface magnetization is the same, so the amount of flux being cut by the loop will be the same no matter what experiment you do, because it's moving through that same little distance. Now, I'm not changing the number of turns in, I'm keeping that constant as 1200 in my case, but whatever you're doing, it'd be different. And the only thing that varies is the time it takes for the magnet to traverse that sort of hypothetical delta S part. Okay, so we're getting the maximum EMF, and of course it'll be when delta T is the smallest, because according to Faraday's law, it's proportional to 1 on delta T. So let's have a look at how all this goes together. So there's my formula. So EMF is proportional to 1 on delta T, because I'm keeping N constant, I'm keeping the surface magnetization of the magnet constant, I'm not changing that, and I'm the area that it's cutting through, the area of the basically of the loop, which is probably a little bit bigger than the gap I've got there. Okay, and I've tried to measure it, and you'll see in my measurements in a minute. So we end up with EMF being proportional to 1 on T. Now the question is, how do you measure T, and what will you plot, and so on? Well, we know the velocity when it hits that point there, it'll have to cover the distance delta S in the time delta T. In other words, the velocity is proportional to 1 on delta T. So if the EMF is proportional to 1 on delta T and velocity is proportional to 1 on delta T, EMF is proportional to velocity. Now that's nothing new to you and to students. You'll often see the formula written in this form. Well, that's what I'm saying, EMF is proportional to V, but you will have seen in some textbooks, I've put that in the Oxford text just as an example. It's not a part of the syllabus, so it's not a formula from the syllabus. It's basically a derivation from Faraday's law, and students often learn that and they use it in the external exams because it's a quick way of doing some problems without going through from the start. Okay, so this is what I'm trying to establish. EMF is proportional to V, and to work out V, the final velocity as it hits the magnet, or gets into the magnet, the formula is just from your motion formulas. V squared equals U squared plus 2GS, or V is proportional to square root of S, because U is constant at 0 and G is a constant, acceleration due to gravity. So V is proportional to square root of S. Now we know that EMF is proportional to V, so EMF should be also proportional to delta S. Okay, so if we plot EMF versus S, we should get that square root relationship like that. So Y is proportional to the square root of S. That's what you should see. Now you'd linearize that in physics by just plotting it against the square root of S. You should get a straight line. Now another graph you could do is EMF versus velocity, and you should also get a straight line. So what I'd like to do is to carry out this experiment, get to generate that graph, and then linearize it to see if we get this one, and have a look at that. Okay, so here's the setup again. Same as before. I'm going to drop a ruler. We'll start off at 10 centimeters. Drop a magnet. I'll start off at 10 centimeters. So I'll take this magnet, so the bottom's at 10, and then it'll fall through this loop, and the crow will record it here. Now the image on the screen is just from a previous experiment, so I could clear that, but I just left it there. Okay, so I'm using the 1200 turn coil made by IEC in Australia. They're about $66, and you can buy those from Scientific. There's their website if you're interested. I'm using this Handtech. It's a 20 megahertz oscilloscope, a USB, so it just plugs into the USB port. Works really well. JCar have them under their own brand or under a different brand, about $229, but I've seen them on AliExpress for $104, the Handtech one. I think they're the same. It's just different labelling. Okay, I'm using a rare earth magnet. Like I said, I've painted it blue and red just to indicate the north and south poles, but the top so the poles are on the end. Some of the magnets you can buy have the poles down the sides, but you need one with the poles on the end. Now I bought that from, I think it was from Aussie Magnets, $16. Okay, so looking from above, that's the setup. I'm going to drop the magnet through the hole. I just had a little bit of material here to stop it scratching the bench top. Okay, so here we go. I've just got a little video of this. So I'm going to, there's the 10 centimetre mark. Okay, so I'm going to bring my magnet up to that mark and then drop it. So let's see how that works. And then you can see on the graph it's produced a reading, on the oscilloscope rather, on the screen it's produced a reading. And if I look at those again, I'm getting 4.3 and 5 volts. Okay, now I'll zoom in on that so you can see. Now, depending on the scale on the oscilloscope, mine was 2 millivolts per division, so I'm getting just over 4 there, a bit more than 5 down the bottom. Okay, so the next one I'm doing is at 5 centimeters, and you'll see it's a bit smaller. Okay, now it's smaller because the velocity is less. So 3.3 volts there if you have a look, and oops, and well, that's the only one I'm interested in. The incoming voltage was 3.3. Now if you don't have that IEC type of coil, you can get your own, and I've just used these from JCar. They're $9.95, just an enamel copper wire, 70 turns. You might think, well, 70 turns is not much, but you get quite a good reading even with the 70 turns. So that's the cheap way out. I'll just show you that, like what sort of reading you can get. You can see you're getting an enormous deflection on a microammeter. Now that magnet, 650 millitesla surface magnetization, so it's a rare earth magnet, but anyway, you saw that. Now what I did was that experiment a dozen times to get my data, so you just trust me that I've collected the data, but you can see all the videos there at different heights. And now don't be overwhelmed by the amount of data here. Let me just go through this. This is just my table. So here's the S distance. That's the distance the magnet moved, and I corrected that from the height. You might remember I said I had to add a little bit on from the height of the magnet to get the total distance moved. So that's why I think this is the 10 centimetre here, where I had to add on 1.5 centimetres. Okay, so as the height, well, effectively the fall height increases, you'll notice here's all my voltage. I did 3 trials, or 3 tests for each of the independent variables. So each time I varied the independent variable, I did 3 trials, and there's my average, plus I've got the uncertainty and percent uncertainty. Okay, but what we're really interested in here is the change in S and the change in the average voltage. You can see they're both rising, but the question is, what does it look like plotted? It should be the square root graph, and in fact it is. So you get a lovely square root graph, and you can see I've got the Excel formula has it to 0.550 actually, and so that's indicating a good square root relationship. Okay, the R squared value is nice and high. That indicates that the dotted line is a good fit for the data. So 99.8% of the data is captured by the dotted line, if you like, or by the formula. Okay, so that's the first one. Now the next thing to do is to linearize that. Okay, so we said that it should look like a square root graph. So when I linearize it by plotting the square root of the drop height, I get a lovely straight line. The R squared is really high again, and you can see it's nice and linear. It goes almost through the origin. There's hardly any systematic error there. Now, when I was doing this, I had to work out that 1.5 centimetres I had to add on to get to the centre of the coil. Now, if you don't get that right, you get a little bit more systematic error here. If I didn't add that on, I'd be getting a little bit of a systematic error, so the graph wouldn't go through the origin. But that's all genuine, so I was quite happy with that. So there's my relationship, and the error bars are on there, but they don't show up. So it was a good experiment like that. And I then plotted the final velocity versus the EMF, or the EMF versus the final velocity, if you like, and got a lovely linear graph. You can see it goes through the origin, or almost through the origin. It's only a little bit out. And again, the error bars don't show up. Okay, and so I could write that down. If I was a student writing that down as my result, I'd be saying 2.91 plus or minus 3.9%. Now I worked that uncertainty out in a table before, so there's the uncertainty to do with the gradient, and then plus the intercept and the uncertainty associated with the intercept. Now you could write that down as a percent like I have here, or you could just put it down in this form, okay, where you've got the absolute uncertainty in the gradient. And of course you've always got, you don't have percentage uncertainty for intercepts. That doesn't make sense. It doesn't work, because if you had it going through the origin, it would be infinite. Okay, to move on, so there's the relationship. That's what a student would be writing in their report. And I'll just go through some of the calculations for error. Now this relies on knowing the value of the magnet, the B value for the magnet, the surface magnetisation. Now if you get them from a supplier such as Aussie Magnets or one of the big magnet suppliers, you can get the specification sheet, and it usually tells you what the surface magnetisation is. It'll probably tell you in Gauss, but you can convert to Tesla. If you get them from Bunnings or somewhere like that, they don't often tell you the specifications, and it's a bit harder. You can't do the error analysis. So I worked out what the magnetisation would be at a 14 millimeter distance from the wire. Now I'm assuming this is a bit tricky, but I'm assuming the surface of the magnet is a little bit away from the wire itself. I'm just taking the average value for the radius, and it works out to about 14 millimeters from the middle of the magnet. Now again, that's just sort of predicted numbers or made up numbers, but it seems to work, and it's not unreasonable to do that. So the length of wire was the number of turns, which was 1200 times 2 pi, so 2 pi r. 2 pi r, there should be an r in there. Oh, there's the r value. Sorry, I left the r out. 2 pi r. So I get 162 meters of wire, plus or minus 1.2%, because I'm not exactly sure of the distances and so on. So this is just having a go at it. The gradient for that graph is just the EMF over V, because I plotted EMF versus V, and that should be equal to BL. So B, the surface magnetisation at, or the magnetic field strength at that position of the loop of the coil, is equal to the gradient divided by L. So there's the gradient, which I took from up here from the graph, divide by the length, which I worked out here is 162 meters, and I've got the uncertainties with those. It comes to about 18 millitesla, plus or minus 5%. So that's my experimental value for B, and I can work out the absolute error. It's just the 19 that I worked out from the catalogue or from the specifications, minus the 18 that I got experimentally. That gives me an absolute error of 1 millitesla. Now you can express that as a percent. So the percent error is the absolute error divided by the average value, So that's 1 over, or the accepted value I should say, not the average. That comes to 5.3%. So we can say there's the B is 18 plus or minus 5.3%. That's what I said. So that comes to plus or minus 1 Tesla, a millitesla. So the range for B experimentally is from 17 to 19 millitesla. The accepted value is 19. So my experimental values at the top value of my range is just on the experimental value. So I can say the range includes the accepted value, so the experiment is accurate or accurate enough. Now that depends on a whole lot of things I've sort of predicted and sort of judged the best way I can. But it just gives you a way of working stuff out. You mightn't use that at all. The students mightn't use any of that because they might think, well, I don't know what B is, I don't know what the distance away, I don't know the length of the wire and so on. But anyway, it's just one way of doing it. The second way you can do it is changing the velocity, by using a pendulum. So the further apart, the bigger the displacement you have for the magnet, as it swings over the top of the loop or the coil, it'll have a different velocity. So the bigger the distance, the higher the velocity. And there's a relationship between distance and velocity. So once you know that, you can get your EMF values and plot it to see how it goes. Okay, so I'll just show you one here. So I'll just pull it to one side, about 6 centimetres away, a little white marker stuck to it. Let it go, and you can see it generates a nice sine graph. Okay, so the input side is here, so you'll notice it's small there, and then as it is about the same size as it comes out, about the same. So let's have a look. So that was using a string length of 50 centimetres, and I pulled it to one side 5 centimetres. I said 6, but it must have been 5. And there's a close-up of the graph, and you can get a reasonably accurate reading of the voltage. You can see the line is fairly sharp. The trace on the crow is fairly sharp, and you can get reasonable. There's a little bit of uncertainty in there, but you can judge that. So here's the input side, or the incoming side, 350 millivolts. Okay, now I did that many times and did duplicates and so on. This is all genuine. I did take the results. I was curious to see how it went. Now to try and work out the height that the magnet has fallen through, all I know is the distance across here, the horizontal distance. But there is a simple relationship between it. I won't go through it, but there's a simple relationship between D and H based on similar triangles and so on. Now I'm using a length of 50 centimetres, so the logic is here, and it ends up that H is proportional. H equals D squared. So this value of H equals D squared. Now the relationship between the height and the velocity is just the conservation of mechanical energy one. So we end up with something like that. Half mv squared equals mgh. Cross out the m's, and you end up with v is equal to the square root of gh. Now we know what h is. It's equal to d squared. So you can just plug that in there, and you can get the velocity. So again, don't be daunted by this big table all at once, but basically I've got all these distances that I've pulled the magnet to one side. There's the height in meters, and I've worked out the velocity. There's my readings, the trial tests 1, 2 and 3 for each trial, and there's my average. Now of course what I'm going to plot is the velocity versus the EMF, because that's the key thing I want to look at. They should be linear, so let's have a look. And it looks nice and linear. I can draw a line of best fit through there and put in my error bars and put in the maximum and minimum gradients, or lines of best fit, or trend lines anyway, and I end up with that for the dotted line, the main trend line, but I've also worked out the maximum minimum gradients as well. Okay, so that's here. That's the plus or minus 150 is the maximum minimum gradient uncertainty, and then I've got some uncertainty in the C value down at the end. Okay, so I can express that as a percent. So that's how a student could record that in their report. Okay, now just a couple of other quick ones. If you don't have a digital crow, I was suggesting you can use a microammeter or a millivoltmeter, whatever you like. They both work really well. So I've done the same experiment, except I'm using the analog meter rather than the USB crow. Okay, so here's me doing it again. Pull it to one side. I've slowed the video down so you can see it. Okay, so it swings up to 400 or 500 microamps, and you can use that. You can convert that to a voltage reading. All you need to do is measure the resistance of the coil, and that's not hard using a multimeter. Okay, so that's that, and I was getting a maximum current 415, and so the EMF turns out to be 14.5 just by knowing the resistance of this little coil is 35 ohms. Okay, so I can plot that again, and I get looks like it's going to be a linear trend line, and it is pretty good. I've done the maximum minimum trend lines for that, and I've converted that into uncertainty values down here for the gradient and the y-intercept. You see a little bit of uncertainty there, a little bit of systematic error. Now, I'm not sure where that's coming, probably from not knowing exactly when the magnet is over the top of the loop, the coil rather. Anyway, that's how it all works. So I've presented that as a percentage as well. So as well as having the EMF in absolute terms, I've presented as a percentage, but don't forget the uncertainty for the y-intercept is always left as the absolute value. Okay, look, just a couple of things. This is quick. If you have the cathode ray oscilloscope rather than the USB ones, the digital oscilloscope, you can do the same experiment. Look here, I've just got a pendulum with a couple of magnets. I'll just use a little hexagonal nut to stick so that the string is held on the surface to act like a pendulum. I'll use a bit of plastic in between, make it easier to separate them. But look, here we go. All you need to do is video that, and then I've got a ruler in the background, and you can work out the displacement and thus the height and so on. Okay, that's that. And finally, just a quick one. I also have tried EMF versus the number of turns. I keep everything else the same, so the distance, the type of magnet and so on. I'm keeping the velocity the same, but I'm changing the number of turns. Now I've just used some little bobbins from Spotlight. They're not very dear, a couple of dollars each, and just used some of that wire. So I wound 200 turns on that, did my experiment. Look, there it is side on, you can see all the turns. I made up some 400, so I had 100, 200, 300, 400, and there's my little clear plastic bobbins I used. That worked really well. Here's an example. The trouble is you get it's not a very high voltage, so you get a lot of this interference. The signal is not that clear, but I'll just show you that. Now, when it's a high speed, when you're taking the pendulum a fair distance from the center point, you're getting a reasonably clear graph. But I think I did it again with, now let me see. Oh no, I did it a whole lot of times. You can see, I think I've got a photo where you can see how fuzzy it is. But there's I only did single trials of that. Oh no, I did three trials of each. Got an average and so on. And there's my uncertainty and the versus the number of turns. So I did 6 different numbers of turns, six variations of the independent variable times 3 tests of each trial, if you like. Okay, so I'll just go through. That's just the normal formula for working out uncertainty. And that's just my scale reading uncertainty from the crow. Right? Even when the max and min were the same, you really can't say there's no uncertainty in the reading. It has to be the uncertainty of the instrument you're using as an absolute minimum. So you can't have 0 there really. So I've just used the uncertainty, scale reading uncertainty from the crow itself. Okay, you can see when I'm getting down to 100 turns, you're getting a lot of fuzziness, and it's a bit hard to work out the voltage. So I have to, that's why I'm just using 10 for all of this. Look, at 50 turns you can hardly make anything out. So I'm saying 0, but you know, who knows. And so when I plot that with the uncertainty, the error bars, I get that relationship there. So it says that the EMF is proportional to the number of turns. Now that confirms that aspect of Faraday's law, so that's looking pretty good. And I've done the gradient for the maximum line of best fit and the minimum line of best fit to enable me to work out the uncertainty. That's the uncertainty and the gradient. So I can then report that, well, that's a percentage uncertainty, about 7. It's not too bad for this sort of experiment. You'd hope to keep it down around 5 or under 5, but I'm quite happy with that. So I'd report it as the EMF is 0.4632 times the number of turns plus the uncertainty minus the C value, the y-intercept, and its uncertainty. Or you could do it as a percent. So there's my 7%. Okay, so that's an easy one to report. These don't take long to do. It's a bit tricky with the lower values down here. You're getting a lot of, you're not getting a very clear signal. Now, I read on a lot of sites that there's where the minimum and maximum crossover is called the pinch point. That happens at 310 turns. Now, I've never worked out why the pinch point is important. Someone might be able to say how that is important for these graphs. Maybe it should be, if it's halfway down, it might mean something more about something to do with random errors, or whether there's a trend in the errors that enable you to make some predictions about how you can make changes to the experiment next time. Okay, so that is the website for my physics. You'll see the link to this video on there. Now this is up on YouTube already, so I'll leave it there. So thank you everyone. That's it. I'm signing out. Bye.